In this video, we'll be looking at a few properties concerning the dot product. So we're going to start off with a little warm-up where we do the dot product for a few vectors, and then we'll make some conclusions. So the first dot product that we're going to do is A dot B, and we're just multiplying the x components, the y components, the z components, and then adding the values up. So I'm going to do -4 times 3. That's -12. 3 plus -1, that's -3. And then 2 times 0, which is 0. When I add those numbers up, I get -15. Now, what about if we flipped around our dot product and we wanted to do vector B dot vector A? Well, I'm still doing the same multiplication. I'm still doing 3 times -4. That's still -12. Still doing -1 times 3. Still doing 0 times 2. And since the order of multiplication doesn't make a difference, our dot product ends up being the exact same thing. So that takes us to our first property. The commutative property states that the dot product of A dot B is the exact same as B dot A. All right, next, we're going to take the dot product of a vector with itself. So A dot A. Well, that's going to mean I have to take -4 and multiply it by itself. So that's +16. 3 times itself is 9. And 2 times itself is 4. And that gives me 29. Let me do the same thing, but this time with the vector B. So now I'm doing 3 times itself is 9, -1 times itself is 1, and 0 times itself is 0. And that dot product gives me 10. Now, if you look at these values, I'm just taking the x component and multiplying it by itself. That kind of just looks like x squared. And then the 9 is just the y component squared. And then the z component squared. The only thing that's missing here is having a square root around it, and then that would become the magnitude. But there is no square root. So what we actually get when we take the dot product of a vector with itself is the magnitude of that vector to the power of 2. That way, it's just the part that is inside the square root. All right, next we're going to take the dot product of A with the resultant of B plus C. So I'm actually going to calculate B plus C first. So the vector addition. And I'm going to be doing the 3 plus 5 to get 8, -1 plus 1 to get 0, and then 0 plus 1 to get 1. And now I'm taking the dot product between vector A, which is -4, 3, and 2, with this resultant vector. So let's see. A dot B plus C is going to equal 8 times -4 plus 0 times 3 plus 1 times 2. So we get -30. For the next one, we're going to take the dot product of A and B, which we already have. We already know that that's -15. And we're going to also take the dot product between A dot C, and then we're going to add those values together. So I'm going to put my -15 from over here, because we had already calculated A dot B. And in this bracket, I'll do the dot product between A and C. So that's going to be -4 times 5 for the x components, 3 times 1 for the y components, and 2 times 1. Here we are. And inside the bracket, we end up having -15. So -15 and -15 is -30. The answers are actually the exact same thing. So how does this compare to this? It looks like we just distribute that vector A into the bracket. So this is actually the distributive property. If you take the dot product between a vector and a resultant, it's the same thing as you distributing that outside vector into your bracket. So A dot B from multiplying these or doing the dot product of those plus the dot product of A and C. And this would apply if you had two binomials as well. Okay, finally, we're going to take the dot product when a scalar is involved. And that scalar that I mentioned at the top is just k equals 3. All right, so we want to do 3 times vector A first. And that's going to be 3 times -4, 3 times 3, and 3 times 2. And then we're going to take the dot product between that and vector B. And vector B is 3, -1, 0. So let's see what we get. -12 times 3 is -36. 9 times -1 is -9. And 6 times 0 is 0. And we get -45. Now, how is our dot product going to be affected if we put that scalar on vector B instead? So 3 times vector B. Well, 3 times 3 is 9. 3 times -1 is -3. 3 times 0 is 0. And then our vector A is -4, 3, and 2. Okay, so now let's see. What do we get? 9 times -4, well, still -36. -3 times 3, we get -9 again. 0 times 2 is 0. And we get the exact same value of -45. So we can conclude here that where you put that scalar value will not change your dot product. So k times vector A dot vector B is the same thing as vector A dot k times vector B. But what about if we have the dot product first, which we already know it's -15, and then multiply it by the scalar? So 3 for that scalar times -15, that's the exact same as well. And this is the associative property. So it does not matter when you deal with that scalar multiplication. The dot product will not be affected. So let's use these properties and simplify some expressions. First, we're going to start with that distributive property. Let's expand each of the following expressions. So I'm going to distribute 2 times vector A, and we get 2 times vector A dot vector B, and then we have 2 times -3, so -6, vector A dot vector C. Okay, what about binomial with binomial? So 3 times 4 is 12, and then we'll have A dot A. 3 times 2 is 6, and then A dot vector B. -5 times 4 is -20, and then A dot vector B. -5 times 2 is -10, vector B dot itself. I can collect my like terms here, and I can use the magnitude property to simplify the fact that vector A dot itself is just its magnitudes squared. Collect my like terms, and then B dot itself is just its magnitude squared. All right, let's try the next example. If vector A and B are unit vectors with an angle theta equals 60 degrees between them, calculate the following. Okay, well, I'm going to start with my distributive property here because all I know is magnitudes and an angle, and I cannot add these quickly. I can, of course, draw myself a diagram and do a parallelogram law and find this magnitude, but then if I find that magnitude, that's not going to be the vector, and I need a vector to do my dot product. So the only thing I can do here is use that distributive property to get started. So we'll have 6 times vector A dot itself, 6 times -2, and then A dot B, and then plus A dot B, minus 2 vector B dot itself. Let's clean up a little bit. And when I have the dot product of A with itself and I have that magnitude squared, that's great because the magnitude of vector A is 1. So that I can actually deal with. And then when I collect my like terms here and I have A dot B, that's also no problem because we know that the dot product of two vectors is their magnitudes multiplied and multiplying by cos of their angle. And then again, another magnitude squared. So this is great. I'll have 6 times the magnitude squared. And then I'll make a little note on the side here what our dot product is. So we'll have magnitude of 1, and cos 60 minus 2 times the magnitude of 1 squared. Now we're just cleaning this up. So 1 squared is 1 times 6 is 6. 11 times 1 times 1 times cos 60. Cos 60 is just a half. So we'll have 11 over 2. And then minus 2. That's going to be 4 minus 11 over 2. And if we get a common denominator, that's 8 over 2 minus 11 over 2, which is a negative 1.5. There we are. So we're using that distributive property here plus that magnitudes property. And actually, when I wrote this dot product here, I also used the commutative property because I treated B dot A the same way as A dot B. So I am using quite a few properties here. And even that scalar comes into play. So the associative property is there as well. All right, next example. If the vectors 2a plus b and 1/2 a minus b are perpendicular to each other, and 2 times the magnitude of vector b is equal to 3 times the magnitude of vector a, find the angle between the two vectors. So right now we're talking about the angle between vectors a and b, not the angle between these two vectors because we know they're perpendicular. So the angle is 90. Now, speaking of perpendicular, we also know that the dot product of two perpendicular vectors is 0 because cos 90 is 0. So that lets us start this question off. The dot product between 2a plus b and 1/2 a minus vector b should equal 0. Okay, we've just been cleaning up these dot product expressions using that distributive property. So let's do that. 2 times vector a dot 1/2 times vector a. Well, 2 times a half is 1. So we'll just have a dot a. And then we'll have 2 times -1 and then a dot b plus 1/2 a dot b minus b dot b should equal 0. I'll collect my like terms. I'll bring in that magnitude property. So I'll do -2 plus 0.5. I'll keep the decimal because it's a nice exact decimal, so I don't mind. Okay, so we're not actually given the magnitudes of the individual vectors, but we are given this statement here. So what I can do, I can divide both sides by 2 and come up with an expression for the magnitude of b in terms of the magnitude of a. So 3 over 2, just 1.5. It's a nice decimal. It's exact. I'll keep it like this. All right. So at this point, I can try to make everything about vector a instead of having it about a and b. Now, actually, there's one more thing that I can convert here because I have some magnitudes, but then I have this dot product. I also want to find the angle between A and B, so I need to bring in a theta somewhere. So swapping the dot product with its definition would be great. So the magnitude of A times the magnitude of B times cos theta. Now I have an angle that I can solve for. And with what I have from here, I can replace the magnitude of vector B in both places with that expression. So I'll have the magnitude of A squared minus 1.5 times the magnitude of A times 1.5 times the magnitude of B cos theta minus 1.5 times the magnitude of A squared should equal 0. Now I'm going to clean up a little bit. So we have magnitude of A squared, and then 1.5 times 1.5 is 2.25, magnitude of A squared cos theta minus 2.25 again, magnitude of A squared equals 0. Now, I do need to isolate for this cos theta. So what I'm going to do, I'm going to bring this term over to the other side while I collect these like terms. So 1 minus 2.25. And then I'll bring the negative 2.25 magnitude of A squared over cos theta to the other side, turning it positive. And now I'll divide both sides by 2.25 times the magnitude of A squared, which is wonderful because on the right side, they just cancel out. On the left side, those magnitude squares cancel out, which is perfect because now I just have a nice ratio that is equal to cos theta. I can take a cos inverse of that fraction, and then I have my angle, which is approximately 124 degrees. So, to recap, use my distributive property, simplified my expression. I tried to make everything about the magnitudes of A and B so that I can use this relationship about the magnitudes to make it all about one magnitude. And then when I started isolating for cos theta, everything just worked out really nicely because the magnitudes canceled out. And we were left with just a ratio, no more variables besides theta, which let us take a quick cos inverse. Keeping in line with perpendicular vectors, let's find a non-zero vector perpendicular to 2, 1, 0. And is this the only vector that is perpendicular to 2, 1, 0? So again, for vectors, the dot product between this vector and some random vector should equal 0 if they are perpendicular. So let me clean this up a little. 2x plus 1y plus 0z, so I'm not even going to write that, should equal 0. Just going to bring the 2x over to the other side, and I end up with this. So if my vector has this relationship, y is equal to negative 2 times the x component, doesn't matter what z is, that vector will be perpendicular to 2, 1, 0. For example, I'm going to say let x equal 1. If I do that, y is going to equal negative 2 times 1. And z can be anything. And the reason it can be anything is because the minute I multiply it by 0 in that original vector that we were given, I'm always going to get 0. So it's not going to make a difference. So for example, 1, negative 2, I'm just going to put 0, is perpendicular to 2, 1, 0. And this is not the only vector. Any vector of the form x negative 2x, and whatever z wants to be, will be perpendicular to 2, 1, 0. So I'll just make a note. Infinite answers. And a general vector would be x, negative 2x, and whatever you want. Anything. All right, last question. Again, perpendicular. Find a vector that is perpendicular to both vectors A and B. So this time it's not just about one vector. It's about two. So I'm going to say this perpendicular vector, I'm just going to call it vector B, is x, y, z. So the dot product between A and vector B has to be 0, and the dot product between B and vector B should also be 0. Okay, so let's apply that dot product. I'm going to start with A and vector V, so that's going to be 1x plus 5y minus 1z equals 0. And then for B and vector V, negative 3x plus 1y plus 2z equals 0. Now let's see what happens if we try to solve for x, y, and z. So we're going to do a little bit of elimination. I'm going to choose to eliminate the x's. So I'm going to multiply this first equation by 3, and I'll just place it over here. That'll be 3x plus 15y minus 3z equals 0. And if I want to eliminate those x's, I'm going to add my lines, and I end up with 16y minus z equals 0. I'm going to bring that negative z over to the other side. And here's what I get for now. Now I'll take this, because I have nothing else I can really do with it, and plug this in for z in that first equation and see what I get for x. Okay. And x is going to equal, well, that's negative 11y. When we bring it over, it'll be positive. So here's what we have right now. I have x is equal to 11y. Y is just equal to itself, obviously. And z equals 16y. So I have a vector that is all about y. Now, in the previous example, we saw that there were an infinite number of options for perpendicular vectors as long as it was a scalar multiple of that original vector. So I can kind of do the same thing here. The vector v is 11y, y, and 16y. I can treat y just as a scalar. And here we are. 11, 1, and 16 is a vector that is perpendicular to A and B, and I can multiply that vector by any scalar besides 0, and I'll get another perpendicular vector. So therefore, vector 11, 1, and 16 is perpendicular to vector A and vector B. And that's it for some extra dot product properties and mini perpendicular applications.